All right, we're on enthalpy versus internal energy at constant pressure. The first question says, consider the imaginary reaction. And the reaction's delta E is 442.26 kilojoules per mole. What is the standard enthalpy change? Okay, so since they gave you delta E, we're going to substitute 442.26 here. And they want you to solve for the standard enthalpy change. So you're solving for delta H. So we're going to leave that alone. N is the change in the moles of gas. So you'll notice there aren't any moles of gas on the reactant side, but on the product side you have 4 plus 3. So you add up the coefficients. 4 plus 3 is 7. So that means that your N is going to be 7, okay? Now, your R value needs to be in kilojoules because your delta E is in kilojoules. So we're going to be using 0.00831 kilojoules per mole times Kelvin, okay? And since this is 7 moles, that's how you're going to cancel out your moles. And then your temperature, since they're telling you you're at standard conditions, in the text, remember they told you that standard conditions had a temperature of 298 Kelvin, okay? So that's how you'll cancel out your Kelvin. So what I would suggest you do is multiply this out, get whatever that is, and then you're going to add that to the other side, okay? You'll end up getting 459.6. Kilojoules per mole of reaction. Okay? Okay. Question number 2.
Where does the 8.31 joules come from?
This is given to you in the text. It's actually given to you in the practice problem, sample problem just above for the R value on the same page. This is going into the video. Okay, number 2. A cylinder equipped with a piston expands against an external pressure of 1.04 atm. A combusted fuel causes an expansion from 0.243 to 1.650 liters with the emission of 1.553 kilojoules of heat. What's delta E? Be sure to include the conversion factor, 101.3 joules per liter times atm where necessary. Okay. All right, so for this one, you're going to use delta E equals Q minus P times the change in V, okay? And they told you that your Q is 1.553 kilojoules, but it's being emitted. So that means your Q would be negative. So this is negative 1.553 kilojoules, okay? Minus your pressure is 1.04 atm. And what we're going to have to do is you're going to have to use the conversion that they gave you, the 101.3 joules per liter times atm. But since this is in kilojoules, let's go ahead and convert that constant to kilojoules. So that's going to end up being 0.1013 kilojoules per liter times atm. So that can cancel like that, okay? Your change in volume is the final volume, 1.650, minus the initial volume, 0.243 liters. Okay, so multiply all of that out, subtract it. You're going to end up with negative 1.70 kilojoules per mole of reaction. Okay, make more sense? All right, now for number 3. To inflate a weather balloon, you must increase its volume from 0.58 liters to a full volume against an external pressure of 1 atm. The process requires 22.632 kilojoules of work. What is the volume of the balloon? Okay, so what I would do is use work equals negative pressure times the change in volume. They told you that it requires 22.632 kilojoules of work. That's going to end up being negative. And then your pressure is 1 atm exactly, so negative 1 atm. Your change in volume, wait, before that, I've got to convert. I need to use 0.1013 kilojoules per liter times atm, so I can cancel atm out to get me to kilojoules, okay? And then if they want the final volume, that's V final minus 0.58 liters. Does that make sense? Okay. You're going to multiply this out, you're going to divide both sides, and then you're going to add this once you get V final alone. So just to simplify things, you're going to end up getting 224 liters for your result.